guys. Welcome back again, a new video for grade 10 advanced, but now we're going to discuss section number 3 under this chapter titled vibration and waves. So now we are talking, we'll be talking about waves or wave behavior. All right, and here we go. So let's start with this slide here. Let's imagine we have two springs, okay? So let's read together from the beginning. So we have to examine what's happening to a wave that travel across a boundary from one medium to another. Medium again means from one place to another place. It could be from air to water. In this case of the spring, it's the wave going from one spring to totally different spring. So we are talking about two different springs, so two medium. Let's hide this first. All right, so mainly we have two springs with different thickness. So we have totally two different springs where the wave is traveling from the first to another. So what do you mean by incident wave? Incident wave means the wave that's traveling first from the source. Imagine we have a source of wave here, my hand. So the wave will travel to the right and then hit the boundary. This is the boundary where the new medium starts. So this is spring number 1 and that's spring number 2. All right, so what will happen? Part of the wave when hitting the boundary, look at the second picture here. Part of the wave will be reflected, so it will go back. So mainly, that's the main one, the incident wave, it's called incident. And that's called reflected wave. All right, why it's reflected? Because it bounces back, it goes back again. Okay, so what do you mean by the third kind of wave here? So we have the incident, we have the reflected, and part of the wave will be transmitted. Will be transmitted means it will propagate or it will enter the second medium. All right, so do you notice something? That the amplitude or the height of the first or the incident wave is bigger from the height of the reflected wave. All right, let's move on. What if we have a rigid boundary like here? We have a rigid boundary, okay? A rigid boundary, we mean like a wall or like it's attached to something fixed. Can you see the picture? So we have, similarly to the previous slide, we have an incident wave. It goes travel, hit the wall, which is called a fixed boundary or a rigid boundary, and then it will be reflected. It will goes back. You see the arrow? The wave will goes back again. Okay, so that's why we call it a reflected wave. So let's go through the text together. So when a wave pulse hits a rigid boundary, the energy is reflected back. Reflected back means it will bounce back. It will go back again. It will not be transmitted into the other medium. All right, the same amplitude as the pulse of the incident wave. What did you notice? That the amplitude of remember the amplitude from the previous lesson? The amplitude, the height of the wave is equal to the height of the reflected wave. So both amplitude are the same amplitude. But what difference now? Also note that the pulse is inverted. That's the main point here when talking about a rigid boundary. So when we have a rigid boundary, the wave is inverted. So it was up. So here the incident wave, it was going up. When it hit the wall, it will be reflected, and in this time it's down. It's not up anymore. It is down. Okay? Yes. Great. So that was about the rigid boundary. Let's continue talking about the superposition of waves, but let's clean the board first. Yes. So let's talk now about the superposition of waves. What do you mean by superposition? Let's look at this picture here. So every time you're talking about superposition means the wave exists. So we are talking about two waves. Okay, you see here, we are talking about two waves exist in the same place in the medium at the same time. Okay, so let's look here. So we have two waves. We have the incident wave, it's going to the right, and we have another wave, it's reflected wave. So we have two waves that met each other here in the middle. So let's draw it. So we have the first wave, that's the incident wave, it was going that way. We have another one, but it's lower than the first. All right, so they both meet at this point here. And this is what we call as superposition of waves. The superposition of the waves. Why? Because the waves interfere, they come together at the same time and at the same place, as they mentioned here in the definition. Same time, same place. So in this example, let's say the amplitude of the first one, let's say it was 3. The amplitude of the second is 2. So because both of them were up, so the resultant in this case, it will be a bigger wave, amplitude of 5. Yes, but what if, like this example, the first one, imagine the first one, let's erase this, or let's draw another one. So let's imagine we have the first wave having 3 centimeter of amplitude, the other one, and going that way, the other wave is inverted, it's downward, but going in that direction. Okay, so the first one going to the right, the other going to the left. Let's consider the wave here having an amplitude of 1 only, 1 centimeter. Here having 3 centimeter. So what might be the resultant in this case? So we have a +3 and here 1, but it's downward, so it's -1. So the resultant is 2. Why? Because 3 minus 1, the amplitude or the resultant have to be 2 centimeter. So that's what we mean by superposition of waves. Two waves meet on the same place and at the same time, and that's that's the definition of interference. It's a famous word that we'll be using from now on. Interference means when two or more waves, they come across each other simultaneously at the same time. All right. Okay, yes. So, after talking about superposition of waves and still talking about the interference, we have to define two main things here. First one, in the resultant wave, in the example 1 and the example 2, we have something called node. Node, and the other thing is called antinode. So let's imagine this wave here. Can you see it? Let's make it bigger here. All right. So imagine this wave, a normal wave going up and down and having an amplitude, but we have to distinguish two things here. We have what we call nodes, the points that don't move, they are here in the middle. Okay, they are always on the axis. So we have the first part or the first point to note, the nodes. Nodes don't move, they are fixed. They are fixed where? On the equilibrium position, on the x-axis. They are fixed. Okay? Symbol is N. They are nodes. The other part that we'll see it here, it's the antinode. What do you mean by antinode? Antinode is opposite to the node. If node is fixed, antinode, they move the maximum distance. They move the maximum place. So let's go back to this picture here. Let's move back to this one. So here are the nodes. They are on the line. Antinodes are on the maximum position. They are always on the maximum or on the minimum. Okay, they move the maximum displacement. So these are the, what do you mean by antinodes? Okay, so they move the maximum displacement from the middle. Okay, they move the maximum displacement from the middle, wherever, however, the node, they are always fixed on the line, they don't move. However, the antinode, they always move up and down. All right, moving on to the next. We explained this, the node, but we have a picture to go deeper into this node and antinode. But first, let's clean the board. Great, so let's continue. So we discussed the idea of node and antinode. Let's hide this for now. Oops. All right. So let's look at this picture here. Okay, great. So let's discuss it. When we have a destructive interference, when do we have any constructive interference, and when the amplitude are different. So on the first case, in case of destructive interference means, as in this example, the incident wave going to the right, the reflected wave going to the left, they are inverted at the same time. So the first one was up, the other one is down. So when they meet, guess what happens? They cancel the energy of each other. Remember in the previous section, we said that the wave transport energy. The first energy is positive, the other one is negative, so they cancel each other, and that's what we call as node. So we have N. That's what we mean by N. It's a node. N-O-D. It's a node. Okay? And then each wave continue in its previous direction. All right? So it's 4. Picture 4, it's similar to picture 2, but in different directions. All right? So, but the most important part is here in 3. Number 3 in the third picture, where we can see the line now is fixed, as there is no wave, because they cancel each other. All right, what about the second one, the constructive interference? So as you notice here, in opposite the previous one, here both waves were upward, going up. Yes, they are in opposite direction, but both of them having an upward amplitude. Okay, guess what's happening when they meet, when they interfere? In case of superposition, look at the third picture, having a giant wave in this case. Why? Because the amplitude is the sum of both of the waves. So imagine the first one having an amplitude of 2, so it's +2 and +2. So the resultant wave having an amplitude of +4, because the amplitude is additional. All right, and then as a previous scenario where each wave continues going in its own direction. All right, here I forgot to mention here the amplitude is 0, having no amplitude. Why? Because it's a destructive interference. Here amplitude is 0. Here is the amplitude is 4. What about the having different amplitudes? So imagine the amplitude of the first one. Can you notice the amplitude of the first one is bigger than the second? So let's say amplitude of the first one is +2, and the amplitude of the second one is smaller, but it's downward as well. So it's like -1. So because the amplitude is additional, so +2 - 1, the resultant is +1. +2 - 1, the resultant is an amplitude of a value of +1. It's a small wave. Okay, and as previous examples where the waves continue each in its own direction. So what do we have to take from this slide? Again, nodes, did you notice that N always never change, never move, always on the same point? Look at this. here there is n, never changed, always fixed, always fixed. In all cases, n is always fixed. What about A here? Look at A. It was down here, here starts to go up. This is antinode, so this is node, and this is what we call by antinode, A, capital A. Here reached the maximum, it's antinode, and then start to go down again. Did you notice that? So N is always fixed. The antinode, you see, one down, here it's maximum displacement, and then it goes down again. So it's moving up and down, depends on the energy of the waves. All right? Yes, so that's it for this slide. I hope it's recording, yes. Okay, we continue talking about the standing wave. Standing wave. So, yes, so by definition, what do you mean by a standing wave? Let's clean this first. So, what do you mean by standing wave? A wave, when we look at it, it seems like it's fixed. A wave having up and down, having crest and throw, it's moving, but to our eyes it seems like fixed. That's why we call it as a standing wave. So what do we mean by this kind of wave? A standing wave is the interference of waves. Waves means like multiple waves, interference of two, superposition of two waves at least, traveling in opposite directions. Okay, so when two waves, the first one going to the right and second one going to the left, and they meet in the middle. So this will create a standing wave. If you look at this graph here, I want you to notice the green, forget about the red for now. If you look at the green and the blue, you notice that the green is going to the left and the blue is going to the right. They are going in opposite direction. And the red one is the resultant of both of them. The red one is the standing wave. You notice it seems like standing, not moving. It's just moving up and down. I hope you noticed that. So again, the green is going to one direction, the blue is going to the opposite, and the red one is the resultant of both of them. And the red one is what do you call as a standing wave. Okay, so let's read this. So when you further increase the vibration frequency, it produces even more notes and antinodes. So let's look at this graph for now. When talking about the frequency, so the first picture having a frequency of, let's say, 1. Okay, the other one, the second picture having a frequency of 2. Third having frequency of 3. So every time the frequency increase, what do you notice about the notes and the antinodes? The notes are increasing. Count the points, the notes. 1, here is 1. We have another one in the middle, and third one here. We have 3 notes. So notes are equal to 3. Okay? Why? Because I increase the, so node in this case equal to 3. Okay? Frequency is equal to 2 in this case. So let's increase the frequency for more. So F equal to 3. How many notes do we have? 1, 2, 3, 4 notes. And we have here 1. We have 4 notes. So here in this case the node are 4. So you notice every time we have more frequency, that's what they are trying to explain here. Every time we have more frequency, so then we are talking about produce more notes and antinodes as well. Great. We finish about this. Okay, so we are approaching the end of the lesson, talking now about waves in 2 dimensions. Okay, waves usually travel in not only in 1 dimension, they go usually in 2 or 3 dimensions. So example of this water here, the ripple of the water, they are creating ripples in the water. Okay, so in 1 direction it's on the x-axis, so this is dimension 1, and we have the wave also traveling on the y-axis. Okay, that's why we call it the surface of the water. Okay, it's surface of the water. Every time you see this word surface, even in math, so surface means we are talking about 2 dimensions. Okay, so the first dimension, as I said, it's on the x-axis this way. It's even right or left. The other one is going up or down in the picture. Okay, so we're talking about 2 dimensions. So let's read together. Waves on the surface of water, so are a good example of waves in 2 dimensions. Okay, however, they are travel in 2 dimensions. Okay, even more than that, we have something what we call as wave front. It's the front of the wave, or the let's call it the amplitude of the wave. Okay, so as you see here, for every ripple, if you notice, for every ripple there is a boundary for it. There is a boundary for every wave. So this is what we call as wave front, the top of the wave. Okay, it's called a wave front. It's a series of concentric circles. You notice they are circles. Okay, each circle is bigger than the other, called wave fronts. They are centered on your finger. So from the middle, okay, the middle from your finger, okay, create ripples, and the ripple are called wave fronts. Okay. Okay, so now talking about the reflection of 2-dimensional waves. So we discussed already the 2-dimension waves. Okay, what about the reflection of such kind of waves? This is, I think, this is an important slide. Okay, so a reflection means when the wave bounce back from a surface. It could be a mirror or a wall or another medium. So let's go through it together. So talking about reflection of 2-dimensional waves. So as shown in this picture, we have something to learn, or called a normal line to draw. Okay, I will tell you more about that. The normal line, which is drawn perpendicular to the barrier or perpendicular to the wall. So in this picture we have a wall or a mirror. That's it. Here it's the rigid boundary. Okay, a normal line have to be perpendicular to this surface. So perpendicular have to be this way. Okay, so this is perpendicular to the surface. So imagine we have an incident wave. Okay, this is incident. Okay, it will be reflected from the boundary, and don't forget, we have always to draw the normal line. This is what we call as normal line, which is perpendicular to the surface, and let's imagine making an angle, the incident wave making an angle of 30 degrees with the normal line. Okay, how to draw then the reflected wave? How to draw it? How do I know where to draw? Is it this way or that way? How to define the direction of the reflected wave? This is reflected. Okay, so the 30-degree angle between the incident wave and the normal line have to be the same 30 degree also between the normal line and the reflected wave. Okay, and that's what you call as the law of reflection. The angle, this is very important, the angle of incidence, which is in this case 30 degree, is equal. Okay, so you can write the angle, let's write it here. So the angle theta of the incidence is equal to the theta of reflection. Okay, the angle of incidence equal to the angle of reflection. 30 degree equal to 30 degree, and that's what we call by law of reflection. Okay, so we learned from this slide 2 things. We learned about the normal line, to draw the normal line, and the normal line we have to measure the angle, not from the wall or from the incidence wave. We always measure the angle from the normal line. So 30 degree is equal to 30 degree. Great. Here is another example. If you notice, we have a wave going down. If you notice, the medium hit the boundary, and then it will be reflected back with the same angle, having the same angle. All right, here is another example as well. We have the normal line from the middle. We have the incident wave making an angle. Okay, they call it angle I or theta I, doesn't matter. And then it's reflected having the same angle, I and R having the same value. All right, so finish about talking about the reflection. Now talking about the refraction. Refraction is another behavior of the wave. Refraction means when the wave enter a new medium. So let's look at this example here. We have the incident wave, and then it's not reflected, it will not bounce back, it's not a reflection. The wave continue but into a new medium. So imagine this is in the air, so this wave is in the air, the other wave here is in water. Okay, so imagine a light or a laser light going, it's a wave going through the medium, and then to enter into a new medium, it have to be refracted. It enter a new medium. But guess what? What's the difference? You notice the difference is the direction. The wave were going into this direction. It was supposed to go into that direction, but it is deviated. It is changed direction, deviated from its initial position and going into this line. Okay, and that's what do you call as refracted waves. Refracted waves means a change in direction. Look at this sentence, a change in direction of the waves of at the boundary between two different mediums. So this is known as a refraction. When the wave change its direction. Okay, so this is called a refraction. All right. This is an example of refraction as well. You see the wave we're going through directly, and then if you notice, it starts to go down a little bit. You notice that? So this is a good example of refraction as well, where the wave change its direction. So let's start solve some of the questions. Here we have first question, talking about characteristic of the waves. So let's read together. So, which characteristic remain unchanged when a wave cross a boundary into different medium? So, a wave cross a boundary to a different medium. So we are talking about refraction, as of course, as the previous slide. We're talking about refraction. So, is it the frequency, amplitude, wavelengths, velocity, or direction? So, what about the frequency? Frequency does not depend on the medium, it depends on the source of the wave. So the frequency remain unchanged, not change. Okay, if we go from one medium to another, the frequency will not change, it will stay the same. What about the amplitude? Amplitude may change, as we saw in the very first slide, if you remember the two springs. Okay, on the first having a high amplitude, when it hit the boundary, it's refracted, or it will continue having a smaller amplitude. So amplitude may change because energy change. So amplitude change because the energy change in the wave. I will keep the wavelengths till the end. What about the velocity? Velocity, of course, will change, because the energy will change, so the velocity is changing. And the velocity depends on the medium. So if I have a different medium, as they are suggesting here in this question, so different medium means different velocity. So velocity will change, of course, as well. So we have the amplitude change, the velocity changed, frequency remain constant. Direction, as we saw in the previous slide, of course, the direction, we're talking about deviation of the wave, so direction will change as well. So what about the wavelengths? Okay, remember the equation of the wavelengths where lambda equal v, the velocity multiplied by the frequency. Okay, we said that the frequency will not change, the frequency remain constant. However, the velocity will change. this will change, the velocity will change. So if velocity change, at least one of them will change, at least one parameter is changed, the velocity. So of course the wavelengths or the lambda of course will change as well. And this is the solution for this question. All right, so we continue with the second question. Superposition of waves. So sketch two wave pulses whose interference produce a pulse with an amplitude greater than either of the individual waves. So we are sketching, means we have to draw pulses whose interference means superposition of two waves with an amplitude greater than either of the individual waves. So greater means we are talking about, so because the amplitude is greater, so it's about constructive interference. It's a constructive interference. Okay, so what about this? So we are sketching two different waves. So this is the first one going into that direction. It meets another wave going into the opposite direction. So what might be the resultant wave? It will become a very big, a giant wave. Okay, so this is what we call as constructive interference. It's the sum of both amplitudes. So imagine the amplitude of the first is 2 centimeters, the distance I mean from here to here, and the second one is as well 2 centimeters. So the resultant wave having an amplitude of 4 centimeters. Okay, so that's what about sketching. We have to draw this diagram. Okay, so the resultant amplitude having a greater than either of the individual waves. Let's go to the next question. The wave change direction as it passes from one medium to another. Can two-dimensional wave? Okay, so we are talking about refraction. Okay, because talking about two different mediums. So the wave change direction, so it's about refraction as it passes from one medium to another. Can two-dimensional wave cross a boundary between two medium without changing direction? So can a wave go from one medium, let's say from the air to the water, without changing direction? Yes, this is possible, but if at only one condition. So imagine this is the air and this is water and this is the normal line. Remember, every time you are sketching waves, you have to draw the normal line. Normally, what's happening when a wave go through making an angle with the normal line, okay, the wave will change direction. This is normally happening. It will not continue straight as this line. It have to be deviated, okay? But at what condition the wave is not deviated? What's the condition when the wave is not deviated? When is that? So when the wave is going straight down. If the wave is going straight down with the normal line, like this example, the wave will continue straight, okay, without making any other angle. Only in that condition, when the incident line, let's write it here, when the incident wave, this is the only condition, when the incident wave is traveling parallel, this is parallel to normal line. Only in that condition, the wave will continue without changing direction, no change of direction. All right, other than this, the wave will change its direction. All right, I think that's it for tonight, for today, and see you in the next video talking about the next chapter.